To graph this log function, I'm going to use transformations. So I need to know what the parent function looks like. I see we have log base 4 here, and we do have an x, but we do have some things that are being added or subtracted. So the equation of our parent function for function g would be y is equal to our log with our base and an x. Once I know what this graph looks like, then I can use transformations due to the +2 and the +1 that are there to take this graph and move it into the correct position. These parent functions all have some things in common. To quickly graph them, you need to know that all of our log parent functions have an x-intercept at 1. They also go through the point base comma 1. So for this particular graph, we have a base of 4 here, so it's going to go through the point 4, 1. And then we also have a vertical asymptote right on the y-axis, and the equation for that would be x is equal to 0. So if I make a quick sketch of the parent function, it would look like this. The equation y equals log base 4 of x is one of the parent functions, and it has an x-intercept at 1, goes through the point 4, 1, and again, the reason the x-coordinate there is 4 is because of the base is 4, and then we do have that vertical asymptote right on our y-axis. Our graph's shape will start at the bottom here, very, very close to the asymptote, a little over to the right of it, and then go through these points using a curved line in a logarithmic type shape. So that's a reasonable sketch for the parent function. What we need to do is take this function and, using transformations, come up with the graph of function g. In this equation, we have some addition in a couple of different places. On the end, we have a +1, and inside the parentheses, we have a +2. Any addition or subtraction in grouping symbols is going to slide the graph either to the left or to the right, and plus does go to the left. So we will need to slide our parent function graph over to the left 2 to get function g. And we're also going to need to move it up 1. If you have any addition or subtraction outside of grouping symbols, that's vertical shift, pluses up and minuses down, so the +1 on the end will take the graph of the parent function and move it up 1. So if I take everything here in our graph, the asymptote and the graph itself, take that entire graph, move it left 2 and up 1, then I will have the graph for function g. The other option would be to make an XY table and come up with some values. Okay, so let's take a look at sketching a quick graph. All right, so I'm going to take the 2 points and the vertical asymptote from the parent function, and I'm going to slide those different characteristics of our graph left 2 and up 1. So the first point is at the point 1, 0 on our parent function. We have an x-intercept there. I need to slide that over to the left 2 and then up 1. So that would give us the point -1, 1. I also need to take this point, which is at 4, 1, and also move it over left 2 and up 1. So at 4, 1, that would give me a point about here. I want to go left 2 and then up 1. So that would be the point 2, 2. Guess I should have extended this a little bit higher. So there's height of 1, and there's 2. And then the last thing I need to do is take our vertical line, that is our asymptote, and move that left 2 and up 1. If you take a vertical line and you slide it up or down, it's still a vertical line and it's not going to look any differently, but we will need to slide that over left 2. Technically, we are going over left 2 and up 1, but you just won't notice the vertical shift. So from our y-axis, I'm going to go over left 2 and then up 1. That's going to give me a vertical line that will cross the x-axis at -2. And then from there, we draw in our shape. Graph starts here, close to the vertical asymptote down at the bottom of our graph, and then curves using a log shape and goes through those other 2 points. This is a decent sketch of function g. So, using the parent function with its 2 points and vertical asymptote, and then recognizing what the transformations are, I can come up with the graph pretty quickly. We are also supposed to determine 7 other things. The first 3 are the domain, the range, and the equation for our asymptote. Well, you can look at the graph in order to determine what these different values are. I'm going to start with the asymptote first, and then I'll fill in domain and range. If you look at your graph, you can see that the asymptote has the equation x is equal to a -2. If you don't want to look at the graph and you want to look at the equation instead, whatever your shift to the right or to the left is going to give you your equation for your asymptote. It's a vertical line, so it's going to be x is equal to, and then it will, if it's a horizontal shift here, it will be whatever this value is, but you do have to change the sign because plus 2 actually does go over to the left 2. So even though it's an x plus 2 in the parentheses, our asymptote is at x is equal to -2. So either using the equation or the graph, you should be able to come up with the asymptote. And then from there, this x is a domain value, so I'm going to copy the x and the -2 down. When I take a look at that asymptote, our entire graph is over to the right, which are bigger numbers for x. So x is greater than a -2 is the domain. And the range of all log equations is always going to be all real numbers. These graphs are always going to go down to infinity, -infinity and up to +infinity. So the range is going to be all real numbers on every single problem. From there, we need to go through and determine the end behaviors. So for our left end, when you go over to the left as far as you can go, we're getting really close to the asymptote, which has an x-coordinate of -2, or an x equals -2 for that vertical line. So when you do your left end behavior, you're going to do the limit, and we want to say how far over to the left we can go. And we can go over as far as -2. When we do that, we are getting close to -2 from the right side, from the numbers that are bigger. So I'm going to put a little plus there to indicate we are getting close to -2 for our x values from the right side, from the numbers that are bigger. And when you do that, our graph is getting close to -infinity. It's going downwards for forever. So your left end behavior would be the limit as x approaches -2 from the right side. F of x is equal to -infinity. For our right end behavior, for the right end, our graph does go to the right for forever, and as it goes to the right for forever, the graph keeps going up and up and up. So as x approaches infinity, y is also approaching infinity. So for our right end behavior, we would have the limit as x approaches infinity, as you go to the right, f of x equals infinity. Our graph goes upward. We also need to make a statement about where our graph is increasing and where it is decreasing. One of these answers will be the domain, and then the other one will be none. These graphs increase or decrease the entire time, and this graph, when we travel along the line from left to the right, is going upward, so it is increasing the entire time. So we want x is greater than -2 for that, because we just copied the domain down. Everywhere where the graph exists, it is increasing, and the graph is existing everywhere we have a domain value. And then for our decreasing, we have none. Our graph is not decreasing anywhere on the graph.